Welcome to day 9 of 365 days of RF. Today, we master one of the most transformative revolutions in radar engineering, 5G cellular networks, and Starlink satellite terminals, phased array electronic beam steering. Think about this: traditional radar systems require heavy motorized mechanical pedestals to physically rotate a parabolic dish. But active electronically scanned array, or AESA radars, can sweep a high-gain razor-sharp pencil beam across the sky at thousands of degrees per second without a single moving mechanical part. How is this achieved? The secret lies in progressive phase shifting. Notice the planar backplate housing an 8x8 matrix of 64 microstrip antenna elements. When every element radiates in phase, the waves combine at bore site at 0 degrees. However, when we apply a controlled incremental phase delay, delta phi, across adjacent elements, individual spherical wavefronts combine in 3D space according to Huygens Principle. Where the phase-shifted waves align in phase, constructive interference forms a powerful main beam steered at an angle theta. The governing equation is, delta phi equals 2 pi d over lambda times the sine of theta. To prevent false ghost beams called grating lobes during wide sector scanning, element spacing d must not exceed half a wavelength. In our 3D interactive laboratory, watch how rapid phase shifting allows solid-state beamformers to steer main beams and side lobes instantly across 3D space, enabling radars to track multiple supersonic targets simultaneously.